You're Luca, right? Or who are you? Luca. Okay. Go ahead. Let's talk for today.
PhD, and my PhD thesis is the design of an acoustic quality jet facility and implementation of active flow control solution for jet flows. But first, let me start with a question. Why we cannot have an airport in the city center of Madrid? And I'm going to show you this nice representation. This is the noise footprint produced by an aircraft passing over a city, and you can see the high level of noise that it's creating. And this is a random guy walking through San Diego, pretty annoyed by the noise of an aircraft passing by. And this is where my thesis developed. Basically, if we look at the noise generated by aircraft, basically from the starting of general aviation up to today, we can see that the noise is decreasing a lot, because since the 80s, noise of aircraft became a major issue for a manufacturer and regulators. And as we can see now, we are in stage 5. The noise reduced already like on the order of 80% compared to what it was at the beginning. I mean, considering that this is a decibel scale, so it's a logarithmic scale. And but the target is by 2050 to have a further 65% of the noise reduction. And take into account that up to now, most of this noise reduction is due to the implementation of turbofans, which basically reduce the exit velocity of jet flows. So that was a huge help for reducing the noise generated. But what can we do more? So what you can see here is the noise source generated by an aircraft passing by. This was an experiment done at the Amsterdam airport, where an aircraft was passing by 75 meters per second at the altitude of around 65 meters. And we can identify the main noise sources, which are typically the landing gears, the airframe, the high lift devices, but mostly the engine, especially at high frequencies. So in order to reduce the noise, the problem moves from and consider that in the engine, the noise is mainly generated by the high velocity and temperature flow mixing with around environment. This problem moves to fluid dynamic problems, which is the reduction of jet noise. Now, reduction of jet noise means we need to control it. So, and my thesis developed in this framework. My thesis is mainly devoted to the development of experimental framework for jet noise control. And this is a typical closed-loop control scheme that where we have a physical system characterized by a state, which is X, its own dynamic, which is defined by the function F. Now we can sense in this physical system through sensors that then feed a control law that decide the control actions. The control action is B, and then we can measure how we are acting on the flow by a cost function J. Now, when it comes to the application of fluid flows, the problem becomes incredibly complex because of the high dimensionality of our problem. I mean, like if you want to represent the flow field, you can imagine at the mesh grid of a CFD simulation or at the grid points of a PIV measurement. It's a highly nonlinear problem because of the Navier-Stokes equations. Then there's the issue of where to place a sensor, where to place actuators in order to be effective. And also, when we nowadays with the implementation of machine learning-based control methods, algorithm, we are usually lacking of the interpretability of the solution that our system is finding. Which means that usually we can find solution, but we cannot extrapolate what we discovered also to different applications, to different test cases, which is usually like large-scale experiment. So my main thesis is that I have to develop my framework for control of the jet flows, but also extract the interpretable control solution from what we are going to find. Now, digging into it a bit, starting from the physical system, we started with the development of and implementation of a jet flow facility. So we have the acoustic chamber. We started trying to, the issue here is that we are trying to reproduce a real condition, which is like free without walls. So what we need to do is to reproduce the free field environment that we usually have in nature. So from the point of view of acoustics, what we need to do is to get rid of the reverberation that we usually have inside the room. So that's why we develop an anechoic chamber. From the fluidic point of view, we need to get rid of the recirculation. Why? This is a typical aeroacoustic facility where you can clearly see that there is an outlet of the flow. It means that I have my flow generated inside, but then the flow is convected outside of the anechoic chamber. Now, in our case, as you can see, we have no outlet. So we had to encounter a solution that we found. We basically designed and implemented this kind of jet collector. We basically created a secondary room on the other side where the flow which is coming from the right, is like trapped, is dissipated, and then it's extracted from the top by the air ventilation. And this is basically what we have now downstairs in the anechoic chambers. Special thanks to the AST lab, Professor Chili, and soon PhD student Giorgio for the help in the manufacturing of this object. And then we did, with the help of Ricardo, that you've seen before, we did a characterization of the acoustic properties of the chamber, because it was important to avoid any kind of side drawbacks of the implementation of such another wall inside our room. And the results are shown here. This is just a preliminary result, but it shows us that we can actually have, in the radius of 1.4 meters around the jet, a free field condition, which is what we are looking for. So, which means that now our anechoic chamber is ready to be used for jet aeroacoustic studies on jet flows. And the results will be presented by Ricardo at the AEROSPACE conference in Rome. Moving next, control law. As I said, usually implementing machine learning, we are losing interpretability of the solution that we are gonna get. So, in order to get interpretability, last year I focused mainly on flow estimation. What does it mean? It means that usually in an experimental setup, you have like a jet flow shooting from the left to the right. We place probes, which are in this case 5 hot wires, which are velocity probes, that provide you with a point-wise measurement, so all in a point, but with a very high temporal resolution. On the other side, we can have PIV. So PIV provides us with topological information. It gives you the whole flow field of the jet, but usually you are missing the temporal resolution because it's not possible to have technologically time resolution high enough for the jet flows. So what we tried to do was to combine the two kind of measurement in order to reconstruct what is happening in the beginning. So basically with PIV measurement by time to time and a continuous stream of the sensors. That's what we call enhanced time resolution of PIV. And these were the results that I presented last year at few conferences. And as you can see here, there is like the original flow field on the top, the estimation from 8 microphones placed around the jet, and which is pretty good, but there's still some work to do. This was regarding the interpretation of the control actions. Then we come to the actuators. We're saying that we need to act on the flow. It's important to have an idea on how we want to act on the flow. So first thing we did was we tried to understand what is generating the noise inside the jet. There are important energetic structures inside the jet. These are the two most important ones. These are like axisymmetric structures. And we have also from theory like noise prediction models like this one that was developed by Morris in 2002. So what we tried to do just recently was we basically managed to get from the models an idea of which are the characteristics of the main structure generating noise in a jet. We came out with this pretty nice scheme that tells us, depending on the Mach number that you see here, the different colors, the main source of noise, which kind of velocity and frequency they have. We look for this because from this one we kind of find an idea of the range of velocity and frequency at which we want to act with our actuators that had to be designed and implemented on the jet flows. So that's why we came out with the piezoelectric synthetic jets. These are basically this is just a cavity with a membrane on the bottom which is oscillating at a certain frequency, and it's generating a trail of vortices like this in the pictures that is acting on the flow. This is what we have now in our lab and that we tested just a few weeks ago. We are planning to mount 6 of these around the nozzle and act these at the lip of it. And this is the first characterization, which is pretty good, which is what we're looking for. Basically, we managed with this kind of device to provide with a velocity at the exit of 10 to 15 meters per second at very high frequencies, like from 500 to 2 kilohertz. And this is what we're going to implement. Lastly, I want to talk for the minutes I've left about the sensor, how we're going to sensor to the flow. As I said, in closed loop conditions, talking about fluids, you need to act very fast because flow at high Reynolds number, usually the dynamics acts at a very high velocity, at a very high frequency. And so if you want to act at a very good frequency, it means that also you need to sense even faster than what you want to act. So what is typically done, it is that are implemented like point-wise sensor, like what I showed before, can be microphones, hot wires, velocity probes, which again provide you with all information in one point, and then depending on that, you can decide how to act on the flow. Now, PIV will be the perfect solution for that if we are able to get real-time particle image velocimetry. Because with that, you can get topological information, you get the full the dynamic of an entire volume or like plane of the flow. And with that, it's probably it's likely to increment the control authority of your actuators, find out new control options. Now, the big bottleneck of real-time PIV is the acquisition of images. And the processing is already pretty fast, but the acquisition of images and the amount of data that you get is typically too high to have real-time PIV, which nowadays it's been tried, but still with a lot of trade-off in terms of accuracy and resolution. Now, what we discovered just like last year was a new technology which is called event-based camera or dynamic vision sensing. It is a completely different approach to imaging, which is usually when we talk about imaging, you can see like here on the top, this is an example where you have a rotating pinhole, and you have a normal camera. What it will do when the pinhole is rotating is just taking frames at a fixed frequency. It is taking frames, and so you can see here what happens. Like this is rotating, and you get this. With event-based camera, what you get is that you get only an activation of the pixel that see a contrast change of the image of the environment. It means that you get many advantages, like for example the sparsity of data. It means that when this is not rotating anymore, the event base is not seeing anything. You don't have any more redundant information. And when you have very fast movement, you get blurred images. In our case, you get still this continuous stream of information. Now, why do we really like this technology? Because, as I said, it reduced a lot the amount of data that you would get from common PIV images, and also it is extremely sensitive. It means that when you want to do high-speed PIV, you usually need high powerful laser because you need to see the particles at a very high frequency. In this case, the sensor is able to react at very small contrast changes, which makes it pretty interesting for our application. That's why we tried this kind of new technology. We compared the event-based camera to conventional PIV camera. I did this experiment with synchronous measurement of the jet flow, which is here, between the conventional camera and an event-based camera, in order to understand if the dynamic of that the event-based camera is catching is the same of a conventional PIV camera. And the results are pretty interesting. It shows that it is able to very, very well follow the same dynamic of conventional PIV, which gives to us a good hint that we can try to implement this kind of technology for real-time PIV measurement to feed it back on the control loop. And these results will be presented at the conference this summer. Now, lastly, just a timeline of what we are doing. So we just implemented our jet facility. Now we got it completed, especially in terms of the anechoic chamber. I'm finalizing the implementation of all the actuators and the control loop, and hopefully by the beginning of next year, we're going to be able to start really to control the flow and see what happens with the hope of implementing this new technology. These are the few outcomes, and thank you for your attention.
Perfect.